So question 5 is describing how to get this graph, a nice view of this graph. Your calculator, that's a TI-84 calculator. We've got this nice view from our table, but knowing how to do what they're doing in graphing calculator is important. So the equivalent of what they're doing would be to click this graph settings and to mess with the values here. So if we put in the practical domain that we wrote back in question 4, we said x was 0 to 9.52 and y was 0 to 1450. That is a view of the practical domain. Now we might want to zoom out just a little bit so we can actually see where it's hitting the x-axis and where it's hitting the y-axis. Now what the textbook is having you do is put in these values. They want a -10 for the minimum x value, and they want a +10 for the maximum, and then they want -50 for the y value and +14. Positive 1500 for the y value. So here it's nice and simple, and Des knows how to get that. You get to just type it in, and there's this beautiful graph. So 5b says, well, what are some important features of this graph? Well, hopefully you see this is U-shaped. In this case, it's an upside down U. And then it has a maximum value, like the largest y value happens to be this y-intercept in this case, and that's the 1450. And then you should note that values on both sides of the graph end up being equal. So when x is 2, we get 1386. When x is -2, we get 1386 as well. And in fact, that's true for every single point on the right side. There's an equivalent point on the left side. So negative x values give you the same thing as positive x values in terms of the y value. That's called an axis of symmetry, and we're going to look at that more specifically as we move through this chapter. And then this special point where it hits the x-axis, the 0 of the equation, is they're -9.52 and +9.52. Again, remember, in terms of the context of the problem we're working with, the left side, so the negative x-axis, was not useful. But as an understanding of this function, this quadratic function, that's useful information. Okay, so if you look on page 395 in your textbook, we are given all this nice information about quadratic functions. So we're given the word parabola. That's what we call the U shape, or parabola. That's not the way to pronounce it. It's parabola. And it can either open up or down. And they're of a special type of category of functions called the quadratic function. And then here's this nice definition. I'm going to pull it out from there because there's a lot of text in there. And I'm just going to write down the function itself. It's f of x equals ax squared plus bx plus c. This is the standard form of the quadratic function. And these a, b's, and c's, these three things are called coefficients. They are numbers times the variable. And you may be saying, well, that c doesn't have a variable there. Well, we could put one there if we wanted to, and we'll talk about that a little bit later. So they're just numbers. And then this portion right here, this ax squared, that's called the quadratic term. Well, really, let's back up. Each one of these things as a whole, the entire thing, I'll circle them. These are called terms. So they are a combination of either numbers and variables and then arithmetic between those things. And then we define that first term. So ax squared is called the quadratic term because it has the squared portion with it. The linear term is the bx version. And then the c term is the constant term because it is not affected by what x value we pick. C is always C. We could put the term there. We could call it x to the 0 power, but from the last chapter, we know x to the 0 power equals 1, so we don't actually write that here. We always leave it as just C. Okay, so if we look at number 6, we're going to identify the different values of a, b, and c, meaning the coefficients of each of these functions in number 6. So y equals 3x squared is our quadratic function. The a is always the number times the x squared. The b is the number times x. There isn't one there, so it's 0. That's why it disappeared. And then the c, we don't see a number by itself, so it's also 0. So in other words, we could write this equation as y equals 3x squared plus 0x plus 0, but mathematicians don't tend to write this because it doesn't add any extra information. So we write it like this. All right, and then the second one is y equals negative 2x squared plus 3. Well, notice the number times x squared, which we call a, is negative 2. The number times x, oh, there's no x there. Well, we already know what that is, right? It's a 0. And then the number by itself, or the constant term, that's the 3. As before, we could write this as y equals negative 2x squared plus 0x plus 3. That's a valid way to write it. We don't ever do that. Our mathematicians don't tend to do that because this, again, it doesn't add any information. All right, one more. Y equals x squared plus 2x minus 1. This one's a little tricky. I have seen students want to write that a is 0 because they don't see a number there. But because there's an x squared, we know this has to be a 1. And again, mathematicians tend to not write that 1. If you need to keep track of the coefficient of a term that doesn't have a number there is 1, write the 1 there. There's no shame in that. And then C here is negative 1. All right, and finally we have y equals negative x squared plus 4x. So here the a, careful on this one, see it's a negative there. It's not negative, it's negative 1. The b here is 4, and we don't see a constant term. That means it has to be 0. All right. So in question 7, we're going to look specifically what's up with that constant term c. So we're going to go back to our function h of t equals negative 16t squared plus 1450. And let's real quick make sure we can identify the a, b's, and c's. This isn't part of question 7, but it's good practice from what we did in 6. So here a equals negative 16, b is 0 because there's no linear term, and c is 1450. All right, so a says, what is the vertical intercept of the graph? That's our question. Well, a vertical intercept, recall, is the same thing as a y-intercept. So it's the value when x is 0. So we're looking for this. Well, in our format here, the x is really t and the y is really h of t. So what we're wondering is, what's h of 0 using the function notation? Well, let's just plug it in. It might be that we already know this. Ooh, look at that. When I do 0 times anything, even if I square it, it's 0. So that all goes away, and we're left with 1450. In other words, the vertical intercept is 0, 1450. Notice that 1450 is the c value. So it turns out that anytime you're looking for the vertical intercept of a quadratic function, it is 0, whatever the number is for c. This is the vertical, did I say intercept? Yes, I did, and that's what I meant. Vertical intercept or y-intercept. So if we went back to question 6, the vertical intercept for y equals 3x squared is 0, 0. For the second one, this y equals negative x squared plus 3, that's 0, 3. For the third one, that's 0, negative 1, because that's the c value. And for the last one, it's again 0, 0. These are the vertical intercepts. In this case, we could call them y-intercepts because we have y as the equations for them. All right, so question B then says, what's the practical meaning of the vertical intercept in this situation? Recall, this function is the height of the ball at a given time. So we would write this out just like we did the y-intercept of a linear function. We'd say at time 0, the ball is 1450 feet high. That's not how you spell high. We could also say before we drop the ball, the height is 1450. Okay, and then C says, let's predict what the graph of h of t would look like if the constant term 1450 were changed to 800. That is, if the baseball is dropped from the height of 800 feet rather than 1450. We're then going to verify our prediction by looking at that negative 16t plus 800. Well, if we take what I just said, we know what the vertical intercept is going to be. It's 0, 800. So then we know the graph, it'll have essentially the same basic shape, but it's going to hit here at 800. No, what is wrong with me? It's gonna be here at 800. So it'll be a shorter graph. Let's confirm that in Desmos real fast. So here's our h of t plus 1450. I'm going to go ahead and copy this function. So I'm hitting the gear button and I'm hitting copy. And I'm going to rename this g of x so we don't have two h's. And I'm going to change this to 800. And then we can compare the two graphs. There it is, exactly what we predicted. It's unfair because I knew it was going to happen, right? But it's the height of the graph is less. So the highest y value ends up being 800. All right, if you look in the blue box on page 396, it says the constant term c of a quadratic function is always the vertical intercept of the parabola because of plugging in 0 into that function, plugging in 0 for each of these x's. Here I'm pointing back to my paper. There we go. Plugging 0 into each of these x's spits out just c.